Okay. Okay. So, good morning, everybody. Thanks for coming here. I didn't actually submit this talk. Arno submitted the talk. But then he hired me to specifically work on this library. So 3 weeks ago, he asked me whether I could prepare and give the talk on his stead. That was my second day working for him. So now I'm here. I'm going to present the philosophy and history and some of the design decisions we made in this library. The library in question is the core library for ThinkCell. We are a small software company. We mainly do a PowerPoint plugin. We are less than 30 developers working on a 20-year-old mono that has been continuously updated to the latest releases and C++ standards. This gives us the unique opportunity, since we develop the library alongside the rest of the code base, to evolve them at the same time. So usually when you have a library, you do something, you put it out there, you get users, then you learn everything you did wrong and you can't change it because that would break your users. We were able to continuously update them alongside with the use case to get the best possible interface. So the library is on GitHub. You can find that at that URL, and it's also on Compiler Explorer. So whenever you see this little Godbolt icon on the top, you can pause the YouTube video, click there, and play with the example. The library is similar to Boost. It is an extension or complement or improvement of the standard library. It's modular. You can pick individual components and use them together with everything else. And crucially, we do not want to guarantee backwards compatibility, but we want to preserve the chance to evolve the library and make it as good as we can possibly get. So the library contains various components. So for the purposes of this talk, I've split it into 4 parts. And the first part are components that improve C++ as a language. Given all the talks about C++ successor languages, we all know that C++ isn't perfect. And we can fix some of those flaws with creative use of library features. So for example, consider casting. In C, there's only a single cast operator. You can use it to truncate a float to an int, or you can interpret an object as bytes, or you can convert a pointer to a short if you want to, or you can remove const. And those are vastly different things with different safety implications, but they all have the same syntax. So C++ improved on that by adding dedicated cast operations. If you want to truncate a float to an int, you have to use static cast. If you want to change something about the way the object is interpreted, you have to use reinterpret cast. And to cast const, you can remove const. This is already an improvement, but let's focus in on just on static cast, because that alone can do a wide range of things. You can use static cast to truncate or wrap arithmetic types. So if you have a bigger arithmetic type, you can use static cast to convert it to a smaller one. You can also use it to call constructors or user-defined conversion operators. So if you have a class that is convertible to something, you can use static cast to do the conversion. And this can execute arbitrary user-defined code. You can also convert character types to and from other character types, including floats. And the same thing for enum, so you can convert a float to an enum. I don't know why you would want that, but you're allowed to. You can also do cast in a class hierarchy. They are completely unchecked. So you can have a base pointer, convert it to a derived pointer, and just hope it's actually that type. You can also, if you have a void pointer, you can convert that to a T star and back. Note that you cannot, like one of those pointer types has to be void. You cannot convert between 2 arbitrary pointers. You have to use reinterpret cast for that. But void is totally okay. You can also use a move. So static cast to an R-value reference is a move operation. And finally, if you have a no discard function, you can static cast it to void to silence a warning. And all of that, like some of those things have nothing in common, right? The cast to void is something completely different than a cast that can invoke arbitrarily user-defined code. Like they're entirely different things, yet they share the same syntax. So at ThinkCell, we've split it up using our own cast operations. And the core is explicit cast. This is essentially what you want to do with static cast most of the time. It converts a value to some other type, but it only does 4 things. It can convert between classes, if that conversion is safe, more on that on the next slide. It can convert between numbers using a debug check to prevent loss of information. So you can convert a longer into a shorter one, but you get a guarantee that you don't throw away bits there. You can convert between characters, again, with a debug check against loss. And you can convert a nullable type to bool. So, for example, you can cast an optional to bool using explicit cast. And that's it. Those 4 operations cover the vast majority of use cases you want to do with static cast, and we've added debug checks for those. Let's focus on class conversions. So for classes, explicit cast is actually variadic. So it can take multiple arguments and convert them to a class type. And this can be done using a user-defined constructor, a user-defined conversion operator, or aggregate initialization. And finally, we have a special user-defined customization point. So we use explicit cast with that customization point to sort of add constructors to classes that we don't control. For example, with std ranges, you can convert a range to a vector of string by calling std ranges too. Thinkcell, we were able to do that before using explicit cast. So whenever we want to add a constructor to a standard library type, we can add that support to explicit cast to do the conversion. Explicit cast is safe. So when you do a class conversion with explicit cast, we do not allow slicing. So you cannot use explicit cast to get from a derived class to a base. It doesn't allow you to, for example, create a dangling span using a similar concept as the borrowed ranges. So if you have an R-value thing, you cannot use explicit cast to convert that into a span. And likewise, in general, we do not allow reference to temporary. This is controlled using the concept safely convertible to and safely constructible from. They are essentially asking whether or not that conversion is well-formed, and it hasn't been disabled by specializing some trait. So just because something is convertible, it's not necessarily safely convertible, and you can specialize the trait to mark it as safe or unsafe. Explicit cast is the cast that you want to pick by default. But for everything else, we also have specialized cast operations. For example, you can use as unsigned or as signed to convert between signed and unsigned. When you have an enum, you can use to and from underlying to convert between the enum and its underlying integer type. You cannot use it to convert the enum to float, just this single underlying integer type. If you have a class hierarchy, you can use base cast and derived class to navigate it, and this will use debug checks again to ensure that we didn't do anything wrong there. Void cast does a void star to T star conversion. And finally, TC discard is the cast to void. So this covers most of the other use cases of static cast, but we've got dedicated syntax to mark the message. So I said that explicit cast can be used to convert between numbers, but what actually is a number? Well, in C++, we've got integers. The signed integers, the unsigned version of those, the character types, which are considered integers. Note that char and unsigned char and signed char are three distinct types. So signed char is a signed integer, unsigned char is an unsigned integer, and char is either signed or unsigned, but still a distinct type. And finally, bool is also considered an integer. Especially the last one doesn't really make sense, right? Bool isn't an integer. So at Thinkcell, we have used different concepts. So we've got the char type concept, which are just the character types, and then the actual integer concepts. Those are the integers, but not char type and not bool. So actual integer types. And then actual arithmetic are actual integers and floating point. And when I say explicit cast can convert between numbers, I mean actual arithmetic types. So you cannot use explicit cast to cast a bool to an integer. So with to and from underlying, you can convert between an enum and its underlying type. So what is an enum? Well, first of all, we've got the actual enums and enum classes, but we also consider bool to be an enum, right? And there's an enum with two values, true and false, and its underlying type is unsigned char. So you can convert a bool to an unsigned char using to underlying and get back with from underlying. And finally, we also consider the character types to be the enum for those purposes. So each character type has a corresponding unsigned integer, and you can use to and from underlying to convert between like the character and the code unit represents. One thing that's quite annoying about cast is when you have a function that has a very, very long and annoying type, and you want to return something using a cast operation, you have to then repeat that long type multiple times, which is annoying to type. It would be nicer if you were able to write something like that. So just say return and then tc return cast, and it will automatically figure out the type that you want since you specified it here at the top. And something like that can be implemented. The basic idea is to leverage automatic conversion of a class type. So we create this return cast impl which wraps the source value, and then we have a conversion operator to anything that is convertible from the source. Then we just have a function return cast which creates that object. And now if we use it, like say return cast, we will create this return cast impl object. This will then try to be convertible to char, which works using the conversion operator. So we can automatically get a conversion to the type that we specified. This works great until somebody writes a function with auto and uses return cast there. Suddenly we're returning the return cast impl object, which isn't what we want. We want to get this to be a compiler error, since you didn't specify a type there. So we want to prevent, like in general, we want to control what happens with operator auto, so we want to, like some sort of operator we can overload to specify what happens when we do an auto conversion. And in our case, we want to disable the conversion to auto. You always want to specify the target type. This isn't really a thing in the language, but luckily in this particular case, we can work around that. So the idea is we don't want to return the return cast impl from the function, right? This means that somebody didn't specify the return type, so we instead wanted to get a compiler error. Well, and that's straightforward, right? Just delete the copy operator, and so now you can no longer copy it, and thus cannot return it from the function. Except since C++17, we have guaranteed copy elision, so whenever you actually return like a PR value, so a temporary return cast impl object, this can be returned without actually calling the copy constructor, so this just works fine. Which is annoying. So is there any way we can disable guaranteed copy elision in that case? Well, copy elision requires a PR value. So if we somehow turn our PR value into an X value, we're no longer allowed to do copy elision. The compiler has to invoke the copy constructor, which will cause an error. And one way to do this is to call move or static cast it to an R value reference, but that's quite a bit to type. So instead we can overload the unary operator plus to do the cast for us. And now when we do plus return cast, this will be an X value. To return an X value, the compiler has to invoke the copy constructor, which is deleted, so we get a compiler error. So just to remember, like if you want to get an error in case you forgot to specify the type, just be sure to remember that you write this little plus in front of the return cast. This doesn't really work. Yes?
Oh, you may have just answered my question. I'm not sure I understand the user experience of asking the compiler to tell me to make a mistake that I can just go look and see if I made.
Yeah. So like this doesn't really work, that approach. We need to automate the mistake in that case. Yes, exactly. So we can do that by using a macro, right? Just define tc return cast to be plus, call that function. And now when you return tc return cast, this will be the automatic compiler. And I know what you're thinking, like macros are kind of evil, right? Bjarne himself said that almost every macro demonstrates a flaw in the programming language, in the programmer, and the programmer. And this is a flaw in the programming language, right? We want to control operator auto. The programming language does not give us the ability, so we have to work around that. And one way to work around that is by using a macro, right? So it's perfectly capable to use a macro here. In case you want to learn more about macros, you might have noticed that I've specified tc return cast is not a function like macro. It's just the prefix, and then the parents is part of the macro invocation in the user code. It's not a variadic macro that then wraps the argument and passes it on. This is intentional. Consider, for example, a return cast of some very long and complicated expression. Then all of those tokens, if we had a function like macros, would be part of the macro and be added into the macro. This means that for the compiler, they're all on a single line, which can make error messages worse and better debugging experience. So when you write a macro, you want to keep as little as possible inside the macro. So we use just the prefix version to get the minimal macro experience, and then have the regular function call. Okay. Static cast can also do move, and this is the standard library implementation of move. So just static cast to an R value reference. And this isn't ideal either. For example, you're allowed to call that move on a const object. This simply cast it to a const R value reference, which is somewhat useless. You can't move from that. This will still invoke the copy constructor. So it would be great if we were to get a compiler error in that case, so we know that we have to get rid of the const there in order to actually move the object. The second problem is when we have a function that takes an L value reference, we are allowed to call that move, which will then move out from the L value reference. And this might not be nice, right? Just because the caller gave us an L value reference does not mean that we're allowed to completely steal the object away. If the caller wanted us to steal the object, he would have given us an R value reference. So it would be great if that were a compiler error as well. So at ThinkCell, we have got the tcmove macro. This is just the static cast to R value reference, but asserts that it is not const and not an L value reference. If you want to get an L value reference, you have to decide. You can either use tcmove always. This will move away from an L value reference. So you can explicitly say, I know I'm getting an L value reference. I want to steal it anyway. Or you can say that if it's an L value reference, I don't want to do anything. This is tcmove if owned. This will only move it if it's not an L value reference. And in that sense, it does exactly the same thing as stood forward, right? Stood forward, given an L value reference, will return an L value reference, and given an R value reference, it will return an R value reference. And the same thing happens with tcmove if owned. Now that we're talking about references, let's talk about temporary lifetime extension. So consider a function getStrings, which returns a vector of strings. We can call it and store that result in our strings variable right here using a const L value reference. What we cannot do is capture the first element and store that into a const L value reference. So why can we do the first and not the second? I mean, both of those compiles, but the second one crashes. Well, the answer is temporary lifetime extension. So when you have a temporary object that is bound to a reference, it will be extended to match the lifetime of the reference. So the auto const strings reference will be bound to a temporary, so the temporary lives as long as that reference. But in the second case, we're not actually binding a temporary object to a reference because the operator of the vector already gives us an L-value reference. So we're just binding an L-value reference to an L-value reference. Temporary lifetime extension doesn't kick in. And we have a reference to a temporary that is going to, part of a temporary that is going to be destroyed at the semicolon. This thing was fixed in the range-based for loop in C++23. So there's now an exception if you do that sort of thing in the range-based for loop. But if you do it anywhere else, it's still a dangling reference without any help from the compiler. And even if we ignore that, and some must say that L-value reference lifetime extension works in those cases as well, it still fundamentally gives you the wrong type. For example, now we've got our strings object inside the function that returns decal type auto, and then we return that. Decal type auto will look at the type of strings, which is a const L-value reference, and will likewise return a const L-value reference. But now we're returning a const L-value reference to a temporary that only lives inside the function. The lifetime was extended, but only to match the first reference and not the second one that we then return. So this function always returns a dangling reference. The reason for that is that decal type auto gives you the type of the strings object, which isn't actually the correct one. It would be nice if that were just return a value instead, because the reference doesn't live long enough. So things that we do not use temporary lifetime extension. So what do we do when we want to store the result of a call somewhere in a temporary variable? Well, we could use always autoconst, right? Just call a function, store everything with autoconst. But when we have a function like get strings from somewhere else, which already gives us a stable L-value reference, this is an unnecessary copy, right? The object lives long enough, so we don't need to copy it. We can just bind an L-value reference there. So we need to pick the correct one depending on the situation. And to automate that, so the idea is, when we have an L-value reference, we want to keep it as an L-value reference, return const autoref, and otherwise, if you have a temporary or an R value, we want to have an autoconst. And we have a macro for that, tc-auto-cref. So for example, we have strings, get strings, tc-auto-cref. This is a value, so we will get autoconst, which is the correct type and no temporary lifetime extension. When we call get strings from somewhere else, this is an L-value reference, strings, so we will keep it as an L-value reference. And when we use the first thing, first element of the string, this is still an L-value reference, so we're keeping it as an L-value reference. Right? This doesn't help us in that case. And the problem is that the operator of the vector fundamentally lies about the type. Right? We need, it would be nice if it had two overloads. One, when called an L-value, it returned an L-value reference, and one, when called an R-value, it returned an R-value reference. And then it gives us the correct type, and we can do a meta-programming on the type. But in general, this sort of use case requires more cooperation from the compiler, because by default, R-value reference aren't really a proxy for this is a temporary. And just because it's an L-value reference doesn't mean it's not a temporary, which is unfortunate in the language. But if you go down that road, you end up with Rust-like lifetime annotations. But still, things will be consistently work that way. So we use R-value reference when called in R-values, so we can use our macro to give us the correct results in other cases. Okay, any comments on that? Okay, because now let's talk about something completely different. Let's talk about function pointers. Function pointers aren't that great. If you have an overload set, you cannot take their address because it's an overload set. The only exception is when you specify the type, then suddenly you can take the address because the compiler now goes backwards to figure out which function you want, which is kind of weird and the only thing in the language that works that way. When you call all of, passing it the address of isLower. First of all, isLower might be an overload set depending on how many headers you've included before that, which is nice. And second of all, it's undefined behavior to take the address of a standard library function. So you're just not allowed to call that. If you have myless, want to pass it to map, this is fine. It does unnecessary bloat, right? You're storing a function pointer inside the map. If you were to use a lambda, that would be empty. So things that we just do not use function pointers. Instead, we do what many people do. We have a macro to lift a function pointer into an overload set. Right? So given some callable, just create a macro that create a lambda that perfectly forwards all arguments. And yes, we have to repeat. I actually got this actually conditionally now, except there's a typo there. So we have to repeat the expression multiple times, which is annoying. So we have another macro for that. But this is the idea. And now everything just works. You can use it to form an overload set because we never take the address. You can use it with standard library functions because you never take the address. And when you pass it to map, you do not have any bloat because the lambda is empty. The same logic applies to member pointers. Member pointers aren't great either. At least when you have a function pointer, you can call it with the regular function syntax. But when you have a member pointer, you have to use this weird syntax with the dot star, and the operator has the wrong precedence, so you always have to put it in parents. Like, I don't know why that is. So we also have macros for those that lift member function pointer into the appropriate lambda. We've got two versions, one for member data pointers and one for member function pointers. And note that unlike the, for example, regular function pointer, we have to say type, colon, colon, and then the member. Here you could just say dot size or arrow size, and it will work on any size, any type that has a size function. So can you call that function on both std_string and std_vector because it's polymorphic over the type, which is really useful when you combine that with projections. For example, you want to project something, a range algorithm on some member, and you don't need to specify the type of the thing. You can just say project on tcmemfun.size, for example. To work around the member function pointer syntax, the standard library has std_invoke. We likewise have tc_invoke, but it behaves a bit differently. So we first of all, we static assert against function pointers because we do not want function pointers in the library. You have to use the macro. It also static asserts against member pointers because you use the macro as well. And in exchange, it does automatic expansion of tuple-like objects similar to std_apply. So when you have a binary function like add, it takes two arguments. You can call it individually with the two arguments, or you can give it a pair or a tuple or an array, which is really convenient because this is used inside the algorithms. So for example, when you do a TC for each, and then you zip to ranges, you can just pass it a lambda that takes the individual arguments, and it will automatically be unpacked. Very yes.
How do you know if you want to expand the tuple or you want to use the tuple as an argument?
So it just checks which one, like, Svina is.
Okay, so it tries one and then it
yeah.
falls away.
Yeah. Okay. The second part the library has is many small utilities to write more fluent and more expressive code. For example, std_exchange from the standard library replaces a variable with a new value and returns the output. And this is really convenient in cases where you have like a smart pointer. The move constructor, for example, it has to copy the pointer and set it to null. And with std_exchange, you can make it a one-line and say exchange the pointer with null and get the old value. And this is useful in many situations. We love it. We use it a lot. We also have a tc_change, which behaves like a slightly different, but works in a similar way. This updates a value if it's different. So for example, if you have an optional and you want to call reset, if you have a value, you have to set it to false and then call the destructor. And this can be turned into one-liner using tc_change. So tc_change compares the variable with the new value. And if it is different, it will assign it and return that it has assigned it. Otherwise, it does nothing. And you might not like the way I've written this function where we first reset the flag and then call the destructor, because in general, this might not be exception safe. So for example, when you have a function foo, and if it's dirty, like you need to do some work, and if you first reset the flag, this is problematic if then cleans those, because we've already reset the flag even though we were unable to actually perform the work. However, at ThinkCell, we sort of have many code that interacts with callbacks on the PowerPoint event handler and so on. So it might happen that clean recursively ends up calling foo again, and then that would be an infinite loop, because it will just, this will not be an infinite loop because we reset the flag. If we do it the other way around to be exception safe, now we have an infinite loop because we just keep calling clean over and over again. So to get something that is both reentrant and exception safe, you have to reset the flag first. You can use tc_change for that, and then undo the reset in case you have an exception. This is a bit annoying, but it's what you have to do. So this is also why tc_change does the reset first, because we need to have many code that might need to be reentrant, so we guard it against that. tc_change is actually part of a family of functions built around assign better. So the idea is you have a predicate, and if the value is better than the existing value, you do the assignment and return true, otherwise you return false. So tc_change better is just, is it different? But we also have tc_assign max when you want to assign the greater value to the variable, and then branch on whether or not you did an assignment. And this is a small little utility, but it can be really useful. If you've read Elements of Programming, the first chapter talks about transformations, which are functions which take an object and return some new value. And then at the very end of the chapter, they say that you can also write it as an action, which takes a reference and modifies it in place. And they are duals, right? Everything that's true for transformation is also true for an action, and you can convert one between the other. For example, modify takes a transformation and turns it into an action by just applying it and assigning it again. whereas modified takes an action and turns it into a transformation by doing a copy, changing the copy and returning the result. As an optimization, if modified is passed with an R-value reference, we allowed it to steal the result, so we don't need to do the copy and can just return the object unchanged. Now, both of those are convenient in different situations. Sometimes you want a transformation, sometimes you want an action. But if you only want to write one because you don't want to duplicate your work, the action is more efficient. For example, sorting a container in place allows you to reuse the memory, whereas if you had a transformation that would return a new vector, you'd have to allocate new memory and copy things over. So actions in general are more efficient. So at ThinkCell, we only define actions, right? We have a sort algorithm that sorts in place. We don't have a sorted transformation that returns a sorted container. But the same sort of logic applies to iterator increments, right? So we've got the increment of the iterator, which is an action which modifies it in place, whereas the next function is a transformation that returns the next iterator. And we don't really want to use those because we only want to use the action and don't rely on the existing transformation. So we've got a simple macro TC modified. You can use it to turn any action into a transformation. You give it the object, and then you write the expression that you want to do, and it will simply call modified, giving a lambda that will do the thing in place. And that way, if you want to do a transformation, like on a container, for example, to sort it, you can just say TC modified container, please sort it. Or you want to get the next iterator, TC modified the iterator, and increment it by 1. Consider a function that returns an optional result, and you want to unpack it, so either you want to get the value or some fallback value. You can write it using the ternary operator like so. You cannot write it using value or. This is because this will unconditionally compute the fallback, which might be expensive. You only want to do it when it's really necessary. So we'd like to have some sort of lazy evaluation. Right? We only want to evaluate the function argument when it's actually needed. And in the case of value or, this is possible because the implementation takes anything. Right? It takes some generic thing. And then when it's needed, it will convert that to T. So we can leverage the fact that the existence of the implicit conversion that it does here. So we can write a tag object, make lazy, that stores our lambda. And then it is implicitly convertible to the lambda result. And this is done by invoking the lambda. And then we have a macro TC lazy, which takes an expression and wraps it in the tag object. And now when we pass that to value or, the argument itself does nothing. It just constructs a lambda. And then inside the implementation, only when it's actually needed, will we invoke the conversion operator, which will invoke the lambda, which will evaluate the function argument. Coincidentally, I wrote a blog post about that 6 years ago with a very similar technique. ThinkCell predates one. We just independently came up with the same thing. In the particular case of value or, since C++23, it's no longer necessary though. You can just call, so value or TC lazy is or else in C++23. So or else is like value or, but instead of a value, it takes a function, and it will invoke that function, just like we hacked around using TC lazy. Or else is actually part of a family of monadic operations that were added to stat optional. So the first one is, so we already had value or since always. Then we added or else, which takes a function and it will invoke that to compute the callback. We've also got at then. This takes a function. If the optional is engaged, it will invoke that function with the result. Otherwise, it returns null opt. So the function in that case returns some optional u. Transform is similar. It just will wrap the result of the function inside an optional. So the only difference between transform and then is that in and then the function returns an optional, whereas in transform it just returns anything. Those are very convenient, but they only work for stat optional. So at ThinkCell, we've got non-member functions that work for anything that is optional-like. So we've got TC value or, which works for anything that has a dereference operator and a dereference and conversion to bool. So we can use TC value or, optional or fallback to get like a generic value or. We don't have a TC or else because we can use TC lazy instead. So if you want or else, you can just use our TC lazy. And then, TC and then works for any optional. It will either invoke the function or return a default constructed thing. Transform, like we don't have a non-member transform that with the semantics. So we can just take the function and wrap it in make optional using a chain, for example. This is more verbose, but in most cases, and then you have a lambda anyway, so you can just return make optional in the result of the lambda. To look at an example, consider this code, which wants to unsubscribe a user from the mailing list. So we get the user ID, we first need to look up the user. The user might not exist, so we have to branch to get the email as an optional email. If we got one, we want to remove it from the subscriber list. And if the user was actually subscribed, then we want to update some changes and notify that the subscriber list has been changed or cancel any pending emails and so on. And with and then, this can be like the nested ifs there can be a bit improved. So we first want to look up the user, and then we want to get the email out of that user. We have to use make optional because and then requires an optional as the result. If that is still engaged, we invoke the third lambda that takes the email address, we move it from the subscriber list, and this now returns bool. And we sort of consider bool like an optional void. So a bool is like an optional which does not store any data. So we can still use it with and then, we just don't get a value in the final thing. So it's sort of like if. Like if we return true, then we can invoke the final lambda and notify that the subscriber list has been changed. And this can make dealing with optional or optional like types a lot more convenient. The final convenience thing I want to present is this old problem. We have to deal with the bin API a lot. So we get a handle, we do something, and then we close it. This is, of course, not exception safe, so we have to wrap it in try catch and close it multiple times. But this isn't very C++ type, so the ideal solution would be you write your own handle class with a destructor and move semantics. But that gets annoying if it's just a single thing that calls it. So the standard library actually has something built in the TS there. So you can call scope exit, give it a lambda, and this will invoke the lambda and scope exit. I don't know whether any compiler actually implements it. And it's a bit annoying because you have to keep this dummy variable around, right? So think so, we can just use tc scope exit and then braces and then some code. And this code will be executed on scope exit. A simple implementation looks like that. So we've got a tag type which just invokes the function in its destructor. And then we've got a lambda which creates an object of that type. But this macro, like this has a different syntax. You have to use like round braces, round parents inside the macro, which isn't ideal if like you've got many statements you want to execute at scope exit. This goes back to we want to keep the macro as small as possible. So ideally we want to sort of reuse the closing braces. This one, from the lambda, we want to use them outside the macro, so we have to cheat a bit to make that work from the syntax. And the idea is we introduce a tag type which has an overloaded arrow star operator, and then the macro takes no arguments and instead creates the tag type and then invokes that and starts the lambda. And the call side now completes the lambda with the closing braces, invoke the thing which returns the scope exit info. So this is a very nice trick if you want to do something like you only have a macro that controls the prefix or something, but you'd need something to do at the end. So you can use like this binary operator, which is the overloaded binary operator with the highest precedence that is possible. So you can use that to sort of like do some neat tricks with macros in case you ever want to. So that's and the end result, like it almost looks like a built-in language statement.
You know, I mean, you hide it completely, but is your scope function thing move only?
Yes, it's, or rather it's non-copyable, since you can't access the variable anyway.
Well, if you use the macro.
Yeah, you're kind of supposed to use a macro. Yeah. Okay, so the core of the library, and this is what it started about, is an alternative range implementation. So this is some basic code using standard ranges. We get some integers from 1 to 20. We want to filter them using filter, and then we can square them using transform, and then we iterate and print them. And you can write the same sort of thing with thing-cell ranges. Looks very similar. The main difference is that we do not have the pipe operator, like we don't overload it. We were hoping for a language solution instead of having to add all that infrastructure and complexity. And instead of a range-based for loop, we always use TC for each. More on that later. But otherwise, it's the thing. It's the same. So what's better than the standard library there? Well, for that we have to answer the question, what is actually a range? And in the standard library, a range is defined by iterators. You have begin and end, and those are ranges. But at thing-cell, we've got two more kinds of ranges. We've got generator ranges and index ranges, and they're really useful. Let's start with generator ranges. So a couple years ago, Eric Niebel wrote a blog post about standard ranges where he had this example that computes the Pythagorean triples. And this caused a bit of controversy because of the added, like this is a lot more complex code for the compiler than the equivalent code using just quite the three for loops. Compilation times increase. The optimizer has more work, so this was a bit of drama at that time. And the reason for that is that this sort of code isn't really well suited for iterator ranges because of external versus internal iteration. So iterators are external iteration, where the caller controls the iteration, which is very convenient. The caller can stop at any time, request a new argument, has full control. But when you have actual loop inside the iterator, they need to be awkwardly split. You need to create a state machine and so on. In contrast with internal iteration, you just have a function that contains a loop. This is much more convenient, but the caller doesn't have any control over it. Coroutines sort of combine the advantages of both. You can just write internal iteration, but with the control of external iteration. So with coroutines, the code looks like so. We return a generator of tuples. We just write the 3 for loops, the if, and then we yield each thing. And now the caller, like this can still be turned into iterator, so the caller still has full control, can stop at any time. However, coroutines aren't that great for this particular simple case. They require heap allocation unless that can be optimized away. The compiler, like it's a bit opaque for the optimizer because it's split into multiple functions. It's still a state machine fundamentally. And requires that the coroutine is in the entire call stack. So if you want to co-yield from within a lambda of a standard algorithm, you just can't do that. You have to manually write the loop or call a coroutine a generator aware standard library algorithm, which is a bit annoying. So I think we have generator ranges. So generator range is simply a function that returns a lambda, which takes a sink. And then we just write our 3 loops. And instead of calling co-yield in the generator, we just call tc-yield, give it the sink and the value. And then we can just write a for each loop over all Pythagorean triples and print them. Except that this is an infinite loop, because like this function is an infinite loop. It just calls yield for forever and ever. So can we control that? We control it by returning either break or continue from the lambda. So we only want to print the first 10. So if we reach 10, we return break. Otherwise, we return continue. And all the magic happens inside this TC yield. So the TC yield will then detect a break or continue and abort iteration accordingly. And the implementation is not that difficult. So we've got a lambda, break or continue, and then a function continue if not break. This takes a sink and invokes it with arguments. If the result of the sink is already break or continue, we just forward that directly. Otherwise, we assume that we always want to continue. Then we have a macro that just checks whether something is break, and if so, it forwards it out and returns break. This is similar to like the Rust try operator. So when we have some sort of error condition or break, we want to return from the function. We don't have that in C++, so we have to use a macro. And then yield is just continue if not break, and then return if we did. And what I've omitted here from the slides is an optimization we do. So for example, continue if no break. If it unconditionally returns continue, we return a tag type that says it's always continue. And then in the macro, we check whether we have a tag type so we can eliminate the branch if you don't specify a return value. And with that couple of codes, we can now write generator ranges very conveniently without requiring coroutines, without heap allocation, just functions that take other functions. It's trivial to convert an iterator range to a generator range. You just write a range-based for loop and yield each individual element. But the inverse isn't possible. This is because without coroutines, we cannot build an iterator interface on top. So when we have a range adapter like filter, they provide both the generator interface and the iterator interface. That way we can have the best of both worlds. And the algorithms, if something has a generator interface, it always prefers to call the generator interface because that's more efficient. And the reason it's more efficient is because generator adapters are absolutely trivial, right? This is filter. You just write a for each, give a sink, but only forward the value when the predicate is true. For a more complex example, like this is concat. Just take a couple of ranges and call for each and in each individual one in turn. The only complexity here is that we cannot do like, we want to call for each on each range, but we have a parameter pack, so we just convert them into a tuple, do for each on each element in the tuple, and then we can do for each, but otherwise it's just for each the first one, for each the second one, for each the third one, and so on. Using concat with iterators is really annoying because you have to use like a variant of the current iterator type, and then each increment and dereference has to switch over what's the currently active range, forward that on, and so on. But with generator, it's just like just a bunch of for loops in a row. For the third type of range, let's consider iterators again. So we've got an iterator range with a sentinel and an iterator, and the iterator stores state, so it remembers the current position in the range, but it also has the logic. Like the iterator knows how to dereference itself, how to get to the next one, and how to compare it against the end. So both the state and the logic is stored in the iterator, and the range object itself just provides access to begin and end. So things that we also have index ranges. With an index ranges, we have, instead of an iterator, we have an index. And the index only stores data. It does not store any of the logic. The logic is stored in the range. So the range takes an index and knows how to dereference it. It takes an index and knows how to get to the next one. So all the logic is in the range object. And both of those concepts are equally powerful, right? You can trivially give an index an iterator interface. You just need to store a pointer to the range and then forward to the member functions. And for the other way around, an iterator itself is sort of an index. You just need to provide the interface to call dereference index and so on to just forward to the member functions. So there isn't really any loss of power here by using indices over iterators. But the advantage indices have is that since the range object is required and stores other logic, iterators can dangle, but indices cannot. Like if you have a dangling index after you've destroyed the range, you cannot do anything with it. So it's impossible to dereference an iterator, an index, after the range has been destroyed. Indices are less, yes?
That only applies if the range owns its elements.
Yes,
right?
if the range owns it, like if you have a container.
Then you
Yeah.
still have this problem.
Yeah, yeah.
Right, okay.
Yeah. Since we store indices, we can also store indices, for example, inside the stored vector instead of pointers. And they are less likely to be invalidated. So when the vector resizes, an index can stay valid, but an iterator gets invalidated. We can do efficient bounds checking. So on dereference index, we are inside the range anyway, so we know the entire boundary of the range and can easily ask, hey, are you sure this pointer is still valid, this index is still in a valid position? And finally, it's space efficient when we are nesting adapters. For that, consider filter view. So this is a simplified version of what the standard has. We've got the view, which stores the base view and the predicate. And then each iterator stores a pointer to the parent and the current underlying iterator. Dereference then just forwards, and incurrent just incurrents until we found one where the predicate no longer matches. And so in the incurrent operator, we need the parent pointer to get access to both the end and the predicate of the underlying view. With indices, we can just, like the index is the same. We don't need to store any additional state. And all the logic is different, but inside the logic, we have access to the predicate anyway. So we don't need to store the additional pointer in our index type. So when we have, for example, 3 nested filters, the view itself stores the input and then the 3 predicates. But the iterator stores 3 unnecessary pointers to filter views. The outermost iterator stores a pointer to the outermost filter view, and the next iterator, which stores a pointer to the next innermost filter view, and the next iterator, and so on. So we end up with 3 pointers inside the iterator, plus the actual underlying iterator that we wanted. With indices, the range is still the same. We store the input and 3 copies of the predicate, but the index type is the same. So we don't need to store any additional logic in the index. And when we want to turn that into an iterator, we just need to store 1 additional pointer instead of the 3 additional pointers that we needed. So in deeply nesting many range adapters, we're a lot more efficient. Finally, the standard also has output iterators. Those are iterators that are write only. So for example, we can use it to copy. We have a vector and we want to copy it to some pointer. Since the vector is contiguous and we have a raw pointer, this can be nicely optimized. It calls memcopy, copies everything over as fast as possible. When our input is a DEC, DEC is no longer contiguous, so we cannot call memcopy. This is a bit unfortunate. We have to do element by element copy, even though a DEC, like it has contiguous chunks. Like a more efficient implementation would copy each contiguous chunk using memcopy and then only has a loop for each chunk. When we want to use backinserter to copy something to the end of some other vector, this will call pushback on each individual element, even though their range-based insert is right there and would have been more efficient. So because iterators, output iterators, can only accept a single element, we have a bit of a loss of performance there. So at ThinkCell, we introduced the concept of appenders, which are used instead of output iterators. So an appender can accept a single element, just like an output iterators, but then it can also accept a chunk, which is a range. And the appender can then constrain the chunk as much as it wants. For example, we've got an appender for a vector. The single one takes anything and calls pushback, and the chunk takes any sized range and calls the then more efficient insert, range-based insert. So instead of copy with an output iterator, we use tcappend. Tcappend can append multiple ranges to a container using the appender interface. So it will call customization point object to get an appender and then append each individual range using the appender. And as a bonus, it does explicit cast automatically. So if you have for example, a vector of string, and you want to append like a range of something that can be converted to strings, it will just work because it does calls explicit cast automatically. And all of that logic, the generator ranges, the index ranges. Yes, Tony?
Anything that calls an explicit cast automatically is no longer explicit.
Yeah, sure. Yeah. That's a good point. But we also have a function implicit cast if you want to explicitly do an implicit cast. So like the naming convention isn't really.
All right. That equals it.
Yeah. That is. I ask why it's not just cast, because it's the cast you want to do, right? So all of those logic is built on top of for each. So TC for each is the fundamental algorithm that everything is built on top. That invokes the sync for each element using the most efficient way possible. That is, if sync is some sort of appender, it calls chunk, if that accepts it, so it can get the entire chunk at once, if that's more efficient. If we know like there's a special case for each for this particular combination of range and sync, we've got a customization point object that we can use, like for each impl, that just customizes how for each works completely. If a sync, like if the range is a generator range, we just uses the generator interface for performance reasons, so just pass the sync in, it will be automatically invoked. Otherwise, we try index-based iteration, and if that doesn't work as well, then we use iterator-based iteration. So just does the most efficient way possible to do a for each on each element. So it thinks that we do not use the range-based for loop. This has two reasons. The first is dogmatic. We believe in narrower loops. And when we just have a single range-based for loop, it tends to grow over time, become more complex, and then needs to be turned into an algorithm. So by just not having the loop in the first place, it is more likely that this is going to stay than an algorithm. And the second one is simply pragmatic. The range-based for loop doesn't work with generator ranges, because a generator range requires a lambda, and the body of a range-based for loop isn't a lambda. Like, it would be nice if there was some language solution to automatically like turn the body into a lambda so that it can work. That way you get the nice syntax with the more efficient implementation. So then we've got, besides the adapters, we've got a bunch of algorithms built on top. Some of them aren't in the standard library. For example, we have more container-based algorithms. TC filter in place is the recently added erase if function to just like removes elements that don't match from a container. We've got take first in place to like truncate a container generically. We've got a combination of sort unique of a container, which happens in many cases, and so on. And those are all actions, because you can use TC modify to turn them into transformations. We also have a more flexible find. So find always, the standard version always returns an iterator. And this isn't always what you want. Sometimes you just want to check, is it the element actually there? Sometimes you want the index, sometimes you want an optional. So our find takes return type, where you can just specify what you want. Right? You can say return value or none, which gives you an optional. You can return bool, to just check, is the element in there. You can get the element index inside an optional. You can get a subrange for everything that's before, and so on. So it's a lot more convenient. Just call the find that you actually want in this particular case, instead of getting the iterator and then doing some comparison against that. Any comments about our range library? Okay. So finally, a big part of things, the library is the string handling. And the string handling is quite simple, because strings are just ranges. We do not special case strings in any way. We just treat them as if they are ranges. So strings are ranges, but what's the character type we use? We need to support 3 encodings. We use UTF-8 by default. Then we need UTF-16 for interacting with the Win API. But we also have many ASCII string literals. So ideally, we would just use char80 for UTF-8, char16t for UTF-16, and char for ASCII. This matches nicely, like the number and the character matches the encoding, so which is nice. But in practice, char80 got added. Yes?
So why distinguish between ASCII and UTF-8?
So we distinguish between them for performance reasons.
Okay.
Right? If you have an ASCII-only string, we can pick more efficient algorithms. Unfortunately, we cannot really use char80 because nothing else uses char80. So in practice, we just use char for UTF-8, char16t for UTF-16, except on Windows, where we have to use white char-t, because that's what the Win API takes. But that doesn't leave any type for ASCII, right? Because we're using char for UTF-8 already. So we recently introduced a custom type, char ASCII. This is essentially a strong type for a char that can only contain ASCII values. There's both documents that we are dealing with ASCII, and also asserts in case that we accidentally put non-ASCII in there. And it can be used for optimizations. When we have an ASCII-only string, we can optimize it. So then the question is, how do we actually get a string literal out of char ASCII, right? Because that's not a string literal type. And string literals themselves aren't really great in C++ because they have the wrong type. So they're just char arrays. So when you call size on a string literal, this is 4 because it includes the null terminator. And that's not really great. Also, we don't really have a distinction between static string literal and some temporary character array, which we'd like to do because we use like references as a proxy for lifetime in our conversion and so on. And the value itself is no longer statically known. If you want to append a string literal to a container, you have to use a loop over each character instead of saying, okay, we first append A, then B, then C, because we statically know what the string literal is. So this isn't yet public completely on GitHub because the guy in charge of the library had to prepare a C++Now talk. But the basic idea is to use a user-defined literal that takes the string literal as a template parameter, as a non-type template parameter, so we get access to it as a compile time, and then returns a custom string literal type. This has an end which does not include the null terminator, so the range algorithms just work. And we can also encode the value into the type. So string literal itself can be empty because all the information is stored in the type. This allows us to, when we want to append a string literal, we can do loop unrolling and statically append each individual character, for example. But if we want to get the pointer, we can just reify like a static char array on demand to get pointers to it, which is very convenient. And the encoding of the string literal is controlled by you specifying the prefix in front. So if you say u8 hello tc, this is UTF-8, but the underlying type that we return will still be char, right? Since we don't actually use it, like get any storage out of it, we can just convert the type statically inside the type system. So even though a U8 string would normally be char 80, we can turn that into char at compile time inside the type system. If you use UTF-16, you will get char 16, except on Windows where you get byte char t. And if you don't say anything, this will be a string of char ASCII. That's very convenient. So where do we want to store our strings? Well, we could use std_string, but std_string has a bit weird comparison. So we've got the string A, and then the UTF-8 string A. And does that assertion hold? So is R less than A using strings comparison? It's a 50-50 chance.
Yes.
Yes, it is true. That assertion holds. Okay, so a string is just a container of characters, so let's use a vector of char. Does that assertion still hold? No, because why would I be asking otherwise, right? So, and the reason for that is that char on most platforms is signed, and the UTF-8 values are then in the negative half. So vector just does byte-wise comparison of char, and the negative values are obviously less than the positive ones. So string also has chars which are signed, so we also have negative values, but string comparisons first converts them to unsigned. And then it does unsigned comparison, which is good because that is correct. Like we'd expect it to work that way, but it's bad because that is inconsistent with any other range of char. So at ThinkStyle we use tc_string, which is a string with a different char traits. If you use a tc_string of char, this will use char traits that have the correct comparison. And they're not really correct, they're the wrong one, but they're consistently wrong, right? Which is better in that particular case. If you just use it with any other type, it's the same as std_string. And it's important to point out we only use std_string because we want SSO. We don't want any of the gazillion member functions because strings are just ranges, and why special case like find for a character in a string and not in a container, right? So we just use we ignore all the special member functions, just use it as dumb storage, and use our algorithms if we actually want to find or search things. Likewise, instead of string view, we just use our span, right? Because string views are just strings at ranges, so string view is just a subrange. And note that our span, unlike the standard library one, is just a specialization of the generic subrange view that we already have when the iterator is a pointer. Right? We don't have a distinct type between like a generic subrange thing and span, which simplifies some things. So string arguments are just, yes?
Why not have a small object optimization container?
Yeah, like a small object optimization would be useful, can be introduced, but like that, no. That is less work, right? So yeah. Eventually it makes sense to introduce the container, but I've heard they recently hired someone to work on the library. So That brings us to string formatting. So the gold standard in C++ for formatting is the format library or the subset that has been standardized. You can specify the formatting, like you have a format string, which contains placeholders that you can use to fully control the formatting. Sometimes you also have to use these helper functions. For example, you want to format a MAC address. Thanks, Barry, for the example, by the way. Just copied that from your talk. So you do want to control the range, how it's formatted. So you want to control it as a single thing with colon a separator, and then format each individual element using 2x. And so we've got this mix of the embedded DSL and the custom functions to do the formatting. If you want to add forwarding support for your own type, you need to figure out how many format specifiers you want, how to pass them, and add that logic. And the entire thing eagerly either creates a stored string or pushes it to an output iterator. So at ThinkCell, we do not use that. Instead, strings are just ranges. And when we want to format things, we just want to concatenate multiple ranges. So for example, instead of the first one, we just use concat. We've got our individual parts, concatenate them, and this will generate a range of a single range that contains everything. It's quite efficient because we use generators, right? This is just 3 for loops in a row if you want to get the characters out of it. To do the actual formatting part, we just call functions. For example, asDec is a function that converts a number into a range of characters that represent their decimal representation. And then the second example, we want to format the MAC address. So we first format each individual thing as padded hex, which gives us a range of characters, where each character is each inner range is like the hex representation of unsigned char, and then we just call join to join them all together with a custom separator. And this will then be a character range that we can work with. So we don't have a format string, instead everything is concatenated. So this means we also don't have a DSL, we have normal functions, which is nice because the compiler knows about them. We get auto-completion for the functions we want, we can really conveniently check it and so on. And if you want to add formatting support, we just need to write a function that returns a character range. No need to figure out how many format specifiers we want. We can just pass arguments to that function. And the entire thing lazily describes the entire range and does nothing until it's used. One big advantage of format strings is the ability to use placeholders for internationalization. So for that, we've got TC placeholders. This takes a format string, but it only does the placeholder part. It doesn't do any of the formatting. So it just says hello and then a placeholder, and then we can specify all the placeholders. And if we want to do the actual formatting, this is put outside. This does not contain any of the formatting stuff. So unlike straightforward, this doesn't include the formatting stuff, so the localized strings don't need to include it. Because why would the person who translates all your strings be able to change how the formatting and say in English I want to format it as hex, but in German it should be decimal, right? This isn't really the job of internationalization. This should be put elsewhere. Similar logic applies to files. Files are likewise just ranges. So reading from a file, we have a generator range that gives us each individual byte. And then we can do something with it. We can use range algorithms to parse it and process it and so on. And we want to write stuff where files can be appended. So we can just append stuff to the file. For example, we can append stuff and then use concat to format it. Or in this case, this uses some byte rate, appends just some bytes to the string. And that part is also not yet public. Any comments about our string handling? Okay. Then finally, to close this talk, I wanted to show you some real-world example of how our library is used. So we use C++ for everything. This even includes our website. So we've got some code that turns the list of build numbers that we currently have into the download page. So we've got a list of builds given a major number and a build number and some download URL, and we want to generate HTML that just groups them by major number and then lists each individual build. And the way this works using the range library is like so. So the first thing is we want to group them by the major build number. So we call adjacent unique range, which turns a range into a range of ranges, where each sub-range is equal according to, in this case, the major version number. We then want to convert each individual sub-range into the HTML. So for that we use transform, which invokes the lambda, as I said, for each object. The lambda is invoked with a range, and each range contains builds that have the same major number. We then extract that major version. We just pick the first one, get the version out of it. and want to get the HTML. So we do some formatting using concat. We create the header, contains the version number as decimal, and then the list elements. So we need to then process each individual element. So we want to transform them into HTML representation, again using concat, placeholders with some macro for internationalization, insert the build number, and then render the download link. The entire thing is then joined into a single character range that is returned. And finally, that range in turn is joined and added to the HTTP stream of the website. So this is how we do a lot of HTML generation. That way we just build ranges and then just directly append them over HTTP. So the library has many more features. For example, we've got traits for enum reflection. This allows us to write functions like, is that an enum value? Or we have a generator all values, which generates all enum values. We also got an enum set function, which essentially just turns a bit set. So enums get overloaded. Operators, you can combine them to create an enum. And this works using macros, right? You have to specify macros to opt into that reflection traits. We've also got many specialized data structures. For example, we've got an optional with reference support, which has the correct semantics on assignment. We've got a static vector, which is like an array, like it has fixed capacity but dynamic size, and we're probably going to add like a short string optimized vector as well. We've also got stuff like a dense map, so this maps enum values to things in an optimized way, and so on. So all of that is on GitHub currently. The development is still in our internal monorepo, and I just occasionally copy paste everything over, which isn't ideal. But long term, we will probably move the full development on there as well. If you like this library, we're also hiring. Come talk to me or pick up some of the flyers outside if you're interested. Thank you very much for your attention. You can also find all the slides at that URL. Thank you. Yes.
Yeah, thanks for the presentation. Lots of interesting abstraction ideas, I guess.
Yeah.
It's all very interesting. I just have like a more fundamental question. So when I deal with, like, if I have my internal library with all these utilities, it's very tempting to keep adding more utilities for all these things. In fact, I used to program in Haskell at some point, and my view was that all functional programming languages usually already have a billion of these utilities built into the standard library. If you go back to the HTML generation slide, just looking at this, for someone to be able to interpret this as they come into your organization, there's like a big ramp-up period. I used to love this stuff, but eventually I think like someone changed my opinion that perhaps it's better to keep things more verbose if it lets it be more interpreted.
Yeah. So like the actual function, like this is more split out into multiple functions.
Right.
So then you can give the subranges names, and that makes it a bit more convenient to understand. But yeah, this is like the range-based stuff is always like a bit more. Like if you're not used to it, it's a bit more tricky to understand than a loop. Even though, like, if you used it, you can more easily tell what the loop does.
No, like most functional programmers, for instance, would also write similar code, and they are usually very fluent in writing code like this, which is fine. It just feels like a little more increases the ramp-up period for. I was just wondering, like, what your opinion is about like the benefit of this increased learning curve. So you got an increased learning curve. For being able to contribute to this library. Now, like, do you see? What's your opinion about the benefit you get out of something like this? Yeah, well, I think like there is a cost up front, but I think like once you pay that cost, like there is a definite payoff, right? So I think it's a worthwhile investment to get that to have that cost and.
Maybe I can chime in. Because I'm there for a very long time. So the difference to other organizations like maybe Google or other big open source projects like LVM, who I think intentionally keep their C++ stack very, I say simple without meaning that in a derogatory way. They hire so many people that this upfront cost becomes huge. And we are a pretty small company, and we will not hire 6,000 bachelor students, I guess. And so I think for us, doing that investment into new hires is far outweighed by the increased expressiveness we get. So because we are a few people only, I think it's very important that we have strong building blocks where we can quickly program powerful things without making the same mistakes over and over again. So some of these abstractions, I think you showed it on some slide, that are saying there's a function, there's an algorithm that is sort unique range. That is something I mentioned in my debugging talk. That is something we did so often in our code. That you want to sort a range and then you want to get the only unique elements out of it. And the problem is that sorting and the unique element, they take different predicates. The one takes less and the other takes an equal. We had this 76 times in our code, I think, at the time we introduced the abstraction. And of course, a lot of people had written the predicates themselves, and then they were not consistent, the equal and less. So now we have an abstraction that we have to know about. But if you know about it, well, you use it all the time, and it does the right thing. So that's kind of the trade-off. That is not to say that we don't debate some of those abstractions.
It's just very tempting to keep adding abstractions, and I have like tried to resist that temptation at times, just because if it's like being used in two places, I just like leave it like a for loop, for instance, in my code. That's just how I've dealt with it, but yeah, it makes sense.
I think we minimize the number of abstractions. So that's, for example, this thing that everything is arranged. We use TCppN for everything where we can. That limits the number of abstractions.
Very, yes.
Okay, so I'm looking at some very specific things. So you pointed out that string literals are terrible.
Yes.
And this is something that whenever people try to use ranges, they run into right away. Like,
yes.
You want to pass like a string literal into split, and that never actually does what you want, and then people write angry stack overflow functions that I have to apologize for. So this seems like the kind of thing that, like, so your range abstraction is like very interesting and powerful, but it's very different from the standard library in a lot of important ways. But the string literal thing is like, well, like this is a fairly universal thing that everyone runs into and does just like slot in right away. Is that something that you've thought about, like maybe we need to throw something into the standard to make it easy to make a string literal do what you actually want?
Actually, the stuff about the string liberation, it's not yet, like, currently, they don't work that way. Like, currently we have our own begin and end, which does, like, different thing for char arrays than normal arrays. So like, it's brand new, like last week, I started working on the user-defined string as well, because we want to migrate over to ranges begin and ranges end away from our own. But yeah, definitely, like I've joined the standard committee now officially as part of ThinkCell, so we will come to the committee with some of the stuff that we want. Like, I don't know, like we at ThinkCell, we can say, hey, if you want to use a string literal, just like you don't use string literals with our library, use string literals _tc. Like, I don't know how applicable that is to the standard array. You can just say, hey, you're not allowed to use string literals with the standard array. And like the standard array has a UDL, like you can have a UDL to get like a string view or something, right? Which sort of solve that problem as well. So I don't really know whether the standard is interested or is in a position where it can.
Too bad we just can't change the type of string literals.
Like
stood string literal.
Our TC string, like we are changing it. Right? Okay.
Okay, so I guess I can keep asking things. So,
yeah, sure, no problem.
So the generator thing is super cool, and obviously it's like pretty easy ways to do that. But there's one thing that you can't do with it, which is that if you're in a coroutine and you want to like yield out elements through the generator, right? Now you can't do that. Like, is that something that you just like never run into?
So you mean like we've got like an actual coroutine with a std generator, and you want to combine that with our generator, or what?
Yeah. So like, sorry, right now, if I want to write like for element in like use join to make like a particularly bad one, and then I can like co-yield out of that. Like I can write So that's like not really. I can't do that with like.
You cannot turn our generators into coroutines. Yes. We don't actually use coroutines so far, I don't think. So we haven't.
We do for some servers.
Okay, so we use it for server code, but I haven't run into it. But yeah, that's annoying, I guess. Yeah. Because
otherwise, the only difference is just like syntactic nicety, right?
Yeah.
And how all I can optimize, but this is like an actual.
this is an actual problem. I wonder whether there is like in principle, like std generator, you can somehow get at the promise, pass that to the lambda, and manually call yield value on that. Like that std generator could provide a hook that instead of yield, you can invoke it or something.
You probably have to have some kind of hijacking thing.
Yeah. Okay. Yeah. Yeah.
So you said you don't do backward compatibility, right? So once you deploy your new string type, how long do you think it'll take to modify your entire code base to use it? Or will it break stuff, or do you have a way to mitigate that?
So currently, like for example, we want UTF-16 on Windows and UTF-16 on non-Windows and Whitechar on Windows. So instead of like UTF-16 literals, we have a macro for that. And we can very easily migrate that macro to use the new syntax. We also had like already introduced _tc for ASCII strings. This was a macro before, and it's quite easy to migrate the macro. And then the remaining ones is just a place of so the transition plan is currently we have like begin and end specialized, which return different things. And what I'm going to do for transition is delete them, the string errors, and then just follow the compile errors to figure them out. Yeah.
That sounds like it could still take a lot of time.
Yeah, it can take a lot of time, but it's mostly automated, and like it's a monorepo, right? I can just.
For a lot of the bigger refactorings, we have one colleague who uses libclang to do a lot of those refactorings. I believe automatically, or he's just very diligent. I don't know.
Why didn't you tell, like, I did a lot of refactorings? My hands, you should have told me that.
You're sitting next to him.
Yeah.
For anyone who's looking at your GitHub and it says we don't promise backwards.
Yeah, I know.
There's Git. I mean, you can always use the one you can just pin yourself to. This
exactly. Like you can
be that scary.
Yeah. Right. It's just that internally we want to use the latest version, obviously. But like, sure, like I feel like it's a trade-off that's worthwhile. Like by compromise,
this was Sean Parent's. Like Sean Parent had an internal library at Adobe, which he also open sourced.
Yeah.
Same thing. He would just change it on all the Adobe products. He's like, if you want to use my stuff, like.
Yeah. Like on my first day at ThinkCell, I renamed TC autoshref to get a TC prefix, because it's not public. So like on my first hours I had like an 800 file diff in the project and got merge conflicts with every other developer at the company. So I got really popular there, but yeah.
To add on to that, so I mean, this kind of move fast kind of system does work in a monorepo, which is what most organizations end up using, including mine. But let's say if someone has to use this as an open source project, you could pin yourself to a GitHub version, Git. Unfortunately, it is very helpful to have like a change log associated across versions. Otherwise, let's say I pin myself to something today, and tomorrow C++ 26 comes out. You guys add lots of support for C++ 26 and everything. It's impossible to move to that next version because I don't really know what functions internal behaviors have changed. So, as an open source project, it's breaking change log helps.
Like it's less useful, but like the alternative would be like we want to keep breaking the library to keep it perfect for internal use, and the alternative would be to just not open source it, right? So, which is less useful.
I agree. Like I don't even open source my code, but that's the one thing that probably makes an open source project much more easier to adopt.
It's
obviously. Not like it's your organization's prerogative to do that.
That's what Jonathan said. We should probably develop this on GitHub first, and then include in our repo as a submodule or whatever. Instead of doing it the other way around, which is super annoying.
Like right now, like also on GitHub, like it doesn't have a build system at the moment, but it's header only, so it doesn't matter. But like this sort of infrastructure is currently missing. I need to work on that. Okay. Then thanks for the questions. Hope you enjoyed the talk.